This is a graduate course of solid-state physics. Everybody knows that crystalline is solid, and because solid composed by the atoms, and there are so many atoms in a solid, and therefore it is very difficult to solve the problem exactly. And therefore, the goal of condensed matter physics is to understand how underlying laws unfold themselves in objects of natural world. And the law of great importance of principle of symmetry. And therefore, even though there are many atoms in the solid, the simple way to solve this problem is based on the principle of symmetry. Therefore, I will start from the symmetry. Fortunately, there is a translation symmetry in solid, and the translation means that, for example, if we choose one atom is periodically arranged like this and like this, and there is if we take a unicell, we call this as unicell. Unicell is periodic in lattices. For example, this unicell is repeated endlessly and so on. Therefore, the translation symmetry is very important property in solid. And basically, the translational invariant nature of the periodic solid. Actually, the crystalline order is very simple way that atoms could possibly be arranged to form a macroscopic solid. This small basic unit of atoms repeated endlessly, and the one placed next to the other, so the whole solid can be described completely by studying a small number of atoms, like this kind of small unicell. And therefore, it is very impressive and remarkable that the simple structure model can be used to understand the whole system. Yeah, it is very difficult problem because difficult problem to solve the whole solid, but because of the translation symmetry, we should take only into account very small number of units like a unicell. Why are low energy arrangements of atoms so often periodic? And there is no answer. Nobody really knows about that. The simple explanation is that if there is some optimal neighborhood for each atom, then the lowest energy state for a large number of atoms gives the same neighborhood to every atom. Yeah, and anyway. Then it is a simple idea, but not exact idea. And actually, because of the translation symmetry, these atoms are very, very tightly bound with each other, and there's so many atoms in solid above the Avogadro number. And this small unit represents whole system, equivalent to solving the whole system by solving the small unit of unicell. And therefore, the translation symmetry can be defined like this, and we should define the basis vector ABC, such that the atomic structure remains invariant on the translation vector like this. Here, A direction. In this case, A direction is in here, and B direction is in here. C direction is the outer plane on this screen. Therefore, here the A and B axis, there is a periodic arrangement 1, 2, 3 like this, and a B 1, 2, 3. Therefore, any atoms can be identified by the translational vector like this Rn. Here n1, n2, n3 is the integer number. One can go from any location in lattice to an identical identical location by following path composed of integer multiples of the vector a and b, what I describe here. Yeah, here we should keep in mind that basic building blocks of periodic structures can be more complicated than a simple atom, and NaCl is a salt crystal. It's very simple. It is cubic structure, but many like this. NaCl is very simple cubic structure, but there are many structures, many different structures, and we should take into account that the symmetry, and therefore we can characterize several different crystal symmetry. And for example, in the one-dimensional, crystal symmetry depends on the dimension of the crystal. For example, one-dimensional system, actually there are not many examples in one-dimensional system, but quasi-one-dimensional, and one-dimensional can have only discrete translational symmetry because the arrow becomes right side to the left side from at a certain point, and therefore discrete translation symmetry. But in two-dimensional and three-dimensional case, a crystal can have other symmetries as rotation symmetry, reflections on planes, and a combination of these two operations among themselves, and therefore translation that are not lattice vectors. And therefore, in the there are many symmetries here. Even though there is still exists for translation symmetry, there is we can define that here that this is plane. In this plane, reflection on these two planes can be defined, and the rotation symmetry, reflection symmetry, and so many symmetry can be possible. And therefore, here we define that the space group, and the space group in this case, T means that translational symmetry vector, and R is that rotation space group, rotational vector. Therefore, the complete set of rigid body motion take the crystal itself by taking this space group vector. And here we define that the Bravais lattice. Bravais lattice is our basic building unit of unit cell. How to define that the unit cell on the for whole solid. For example, in a square lattices, and atomic arrangement is very periodic. And in this case, how to define Bravais lattice is one example to define that the unit cell as a definition. It is a definition. And one example is the Wegener-Zeit cell. Wegener-Zeit cell, the procedure is like this. Let's take one atom in here, and let's draw the nearest neighbor. Nearest neighbor from this atom is that one here, 2, 3, 4. There are four sides for nearest neighbor, and bisect the neighbor nearest atom. Then we can define that the closed surface, closed line like this, and we can define that this region is the Wegener-Zeit cell. This is an example for square structure. In the case of hexagonal structure, let's choose one atom in here. Let's choose one atom here and draw line between the nearest neighbor. In this case, there are 6 nearest neighbor. This is a nearest neighbor. And bisect this region, this region, here, here. This is bisect. Therefore, the close this. I'm sorry, my draw scale is not good. And here, this interior region we can define that the veganized cell in the hexagonal structure. And in this case, that this is bisect for this nearest neighbor, and the close line on this case is a veganized cell. Oblique cell also can be defined, and it is a distorted hexagonal structure, and here from a point, and there are also six different nearest neighbor region, and bisect like this, and also we can define that this hexagonal closed region, it is veganized cell for oblique. And the rectangular also square. Rectangular and square is similar with each other, and the central rectangular is kind of hexagonal, also kind of hexagonal structure, and it is a veganized cell. Is one example for representing the unicell. In this case, there is an inversion symmetry, and the inversion symmetry means that R vector should be minus R. This is an inversion. If there is not changed by the if it is not invariant under inversion symmetry, we say that there is an inversion symmetry. Here, 2D lattices are not mathematical fiction. Yeah, there are real two-dimensional materials. For example, graphene and transition metal dichroconide materials, and that they naturally appear as surfaces and interfaces, and like many thin film system, and this is a two-dimensional lattice. Here we define some nomenclature in crystal solid. We define that the Bravais lattice. Bravais lattice is a collection of points in which the neighborhood of each point is the same as the neighborhood of every other point under some translation. Here is the translation is very important. This is a primitive unicell. Primitive unicell is a parallelepiped in three-dimensional form by the primitive lattice vectors, which are defined as those lattice vectors that produce the primitive cell with the smallest volume. Here, the important term is that the smallest volume. Yeah, here is the definition, mathematical definition of the primitive unicell. And the primitive unicell is the A direction, A cross beta C means that this is volume. For example, A, B, C, like this, A, B, C. Then volume means that here like this. This is this volume. A cross beta C means that this volume, it is a primitive unicell. It is ABC means that basic unit vector in a solid that represent the periodic lattice. There are many different primitive unicells. Common features: each set has the same volume and contains only one side of Bravais lattice. Here is one example to define the Bravais primitive unicell is the veganized cell. Here we single side sit in the center of unicell, which is invariant in all symmetry operation that leave the crystal invariant. And the non-primitive unicell lattice region, which can contain several sides, usually has the same point group symmetry as the lattice itself, which produces a full crystal upon reflection. Anyway, you do not care. And here I will define that. I also say about that veganized cell and one unicell, one atom is defined, and here 6 different nearest neighborhood, and the bisect. Yeah, here. Therefore, here this is a veganized cell. In this case, we can define that A1 vector is A0. A2 vector is that half A and A square 3 half, then it is not unique, but different definition can be possible for A1 and 2 can be defined and arbitrarily, but the reason should be reasonable. And anyway, and in this case, N1A1 plus N2A2 equal to 0. It is equal to N1 and N2 should be 0 in this case. Anyway, primitive unit cells also are not unique. For example, primitive unit cell can be choose like this, but you can choose like this also. Also, arbitrarily, you can choose like this, but it should be periodic. The important thing is that the periodic lattice, not a formation, not a shape of the primitive unit cell. And anyway, primitive unit cell put end-to-end field crystal and like a tiling of the plane. And the cells are free to have the rather particular shape as long as they fit together properly. Since they contain only a single particle, the volume of the primitive unit cell of the primitive cell exactly the inverse of density of the crystal. I will describe later what's the meaning of this one, and I will say later. Anyway, it is very important property. Non-primitive unit cell, non-elementary unit cell is a minimal volume of crystal containing several particles, which has the same point group symmetry as the crystal itself, and which produces the full crystal upon repetition. Here, this is a primitive unit cell. Primitive unit cell includes and different species. This blue one and the yellow one is a different species. And if we choose this unit cell, then it can be there are two blue one, two yellow one. It is representative. We can define that this unit cell is a representative to the whole system. But if we find that this kind of this region, it is not primitive unit cell because there are four blue one and one yellow one. It is not a representative for the whole system. In this case, we call it is a non-primitive unit cell. Therefore, we should define that crystal structure that should be represent the whole system. It is very important property. Therefore, the primitive unit cell is very important. Yeah. There are several Bravais lattices. And Bravais lattice is also representing the building block of the periodic system. And for example, cubic structure, tetragonal structure, orthorhombic structure, monoclinic, triclinic, hexagonal, and rhomblohedral. And you do not remember this term, but it is very frequently encountered. Therefore, if we do not know exactly, then when you read many textbooks and read many papers while you're doing the research, and there are many cases. Therefore, you should remind, and also. And many times it is you can see this one, and basically, and the crystal structure is very important because every solid starts from the crystal structure, and electrical property, thermal property, and mechanical property, and optical property like this, and many different properties depends on the crystal structure. Basic property of solid state is the crystal property. Cubic structure is very simple, and A, B, C is equal with each other. A means that X direction, and B direction, Y direction, and C direction is Z direction, and the A, B, C is equal with each other. And alphabet gamma means that here is the A, B, C from the angle from the A alpha beta, gamma, and the O angle is 90 degree. And this is a cubic structure. It is very simple to understand. And you can imagine that the dice. And the dice is cubic structure. And also, in the case, some atom is inside of the cubic structure, we call this is body-centered cubic structure. If the other atoms is in the face in the here is a face, here's a face, in this and face, and if there is atom at the face, it is a face-centered cubic structure. There are somehow FCC structure, face-centered cubic structure, BCC structure, body-centered cubic structure. And tetragonal is similar to the cubic structure, but alpha, beta, gamma is 90 degree, and alpha, beta, gamma are all 90 degree. But AB plane is square, but the C direction is not. C direction is different, and A equal B is identical, but the C is different. It is a tetragonal. Tetragonal is elongated or the compressed cubic structure along the C direction. Therefore, this is a tetragonal structure. Orthorhombic structure is ABC is different with each other. AB plane is not a square, but it's not a square. Yeah, but here A and B is different, and the C also different. But AB and alpha, beta, gamma are all 90 degree. This is orthorhombic structure. Monoclinic is that the orthorhombic structure and distorted along the beta direction. In beta direction, a little bit distorted. And here, in the distorted orthorhombic structure, distorted orthorhombic structure along the beta direction is that monoclinic structure. And also in this case, tetragonal orthorhombic monoclinic case, and here this is body-centered tetragonal structure, body-centered orthorhombic structure, and face-centered orthorhombic structure. And here in this case, two faces, one face, the other opposite face. Only the two face has the atom at the center of base. We call this is a base-centered orthorhombic structure. Here is the monoclinic also can have, there is this base-centered monoclinic structure. Triclinic is more alpha, beta, gamma all not 90 degree. Alpha, beta, gamma are all not 90 degree, and is also more distorted from the monoclinic structure. We call it is a triclinic structure. Hexagonal structure is that this plane, AB plane is a hexagonal structure. AB plane is a hexagonal structure, and C direction is that like a cylinder, and C direction is like cylinder. In this case, alpha, beta is 90 degree, and gamma is that 120 degree, and gamma is that 120 degree, and alpha, beta are all 90 degree. And the rhombohedral is the alpha, beta, gamma, ABC are all identical with each other, and alpha, beta equal to 90 degree, but gamma is not 90 degree. It is also distorted cubic structure. And here, like a distorted cubic structure is a rhombohedral. Yeah. In this case, we can see that the cubic structure is the highest symmetry, and the tetragonal is the symmetry. High symmetry is a little bit broken along the C direction, and this is a tetragonal. Symmetry broken from the cubic structure. Orthorhombic structure is more symmetry breaking along the B direction, and this is orthorhombic structure. And a monoclinic structure is more broken along the beta direction. And this is a monoclinic and triclinic and hexagonal, triclinic up to the triclinic structure, and the more distorted and symmetry becomes lower. And this cubic structure is high symmetry and it lower symmetry, and right. This is a simple characterization of the Bravais lattice in three-dimensional case. That's all.